Okay, hello everyone. Welcome to the Student Show and Tell. Today's session is more for the purpose of the students knowing each other, and and what we'll do is the way we'll run it. Here we have several presenters. Each person can take 15 minutes. I suggest you use the 15 minutes to actually show something. Don't just talk to the void. If you have slides, great. Even if you have an exciting paper of yours that you have worked on and you want to scroll and show us something, that's also fine. Uh, Ideally, what could be good is that you spend the first half of your time explaining things a little more generally, and the second half you can get pretty technical. There is no problem because you'll be surprised that in this school, even though it is a rather diverse bunch of people, almost everyone is really deep into some topic or the other. And you'll be surprised how many people may benefit even from your technical details, although everyone may not know it to the same extent as you. So don't feel shy to do that. Uh, Perhaps if we, I mean, depending on how things go for you, I can give you a warning or something when time is running close to the end. I would say ideally try to finish in 13 minutes and use the 2 minutes for questions. But I mean, since we are not too many, we should still manage. So let's, in order of how I see on my screen, let's just go with Sandra, then Semi, Pavel, Shraddha, and Jacopo. All right, so let's follow that order. Let's get started. Sandra, go ahead. You can all share screen, so do so and excite us.
Thank you. Thank you for being here. So I've just put together a little document of some quotes that I'm gonna read so you can see them yourself. Can everyone see this?
Yes.
Okay, so I thought I'll just talk a little bit about my findings from my PhD research. So as I mentioned at the start of the winter school, I'm finishing a philosophy PhD about causation. And so in this talk, I'll just briefly talk about what I've learned. And please just stop me if I say something that's unclear or something. Um, so that a lot of people are probably familiar with the philosopher David Hume, who's sort of the father of the modern way of thinking about causality in a lot of ways, and that he was a big proponent of this linear view of causation as one event happening after another. And just briefly, Hume was a Scottish philosopher. He's most famous for this book called A Treatise of Human Nature, and he's very interested in the metaphysics of causation. And so he if we go back a little bit further, he wrote um that causality is undoubtedly fundamental to our conception of reality. Like, this has been like a consensus among a lot of philosophers. But what's not clear is that, like, is causality a category that exists in the real world, or is it something that we project onto the world? And there are different interpretations of Hume, but one thing that he's famous for is this view that what it is to say that there's a causal relation between two things is that it's one event that's followed by another event. And one thing that's very striking if one looks at the examples he gives of causation is that he always gives examples of events separated by time. So you see here his quote, he says, priority of time and the cause before the effect. And his classic example is of one billiard ball moving before another. So he says, so this is an example of causation for him. When I see a billiard ball moving in a straight line towards another, even supposed motion in the second ball should be suggested to me as a result of their contact or impulse, may I not conceive that 100 different events might as well follow from the cause? Well, why does he say that? Well, because he sees cause and effect as these two separable events in time. And so you can't necessarily know that the second one will follow. And this famously leads him to the skepticism about causation. So Hume doesn't think that it's a category of the real world, or that's how traditionally how a lot of people interpret him. So for Hume, then the relationship between what we call a cause and its effect is about how something in the past is connected to something that follows in the future. So it's about how we anticipate what will happen in the future based on what's happened in the past. So in other words, this is a linear view of causation. Causes come before their effects. There are also those who argue that the effect can come before the cause, which is also a linear view of causality. But Hume's view, that at least most of the time causes come before the effects, is the most popular view. Both are two-dimensional views. So in my research, I focused on a very unknown philosopher who took neither standpoint, so who thought neither that causes come before their effects, nor that effects can come before their causes. And so that's what I'm going to talk a little bit about. So that's Lady Mary Shepherd, also a Scottish philosopher, very fun. She's, as you can see, she's born the year after Hume passed away, and so she's born in 1777. And very amazingly, she was hardly formally educated, but published a pamphlet about causation in 1824 anonymously. And she was kind of recognized during her day, but then fell out of the picture later. And then she was rediscovered in the 80s, and then now there's a growing interest in her. But it's still very new, and my PhD is the first PhD on her. Okay, so she wrote about causation. So we'll look at her. She gives these two, here are two quotes where she defines causation. So instead of Hume's picture, she says instead, a cause is such action of an object as shall enable it, in conjunction with another, to form a new nature. Another quote, she says, the junction of two or more qualities or objects is wanted to every new creation of a new quality. So instead of this two-dimensional description of causation as one event happening after another that we get in Hume, Shepherd describes causation as a multidimensional phenomenon. It's when two or more things together create a third. Each cause she calls a union that's composed of at least two entities. This is also interesting because traditionally philosophers have tended to view causation as something different from composition. So like something causing something is different from it composing something. But to Shepherd, these are very closely connected. She thinks that whenever anything happens, whenever there's any change, it's caused by at least two other things interacting in this way. She calls it, they're combining in some way. So this is Shepherd's general account of causation that she applies to all areas, including both physical and mathematical examples. So one physical example Shepherd gives is of Newton's second law, which says, no motion would have taken place except from the conjunction of the body and the impulsive force. The idea here seems to be, there's things, the union of a force as it's applied to a mass creates the acceleration. So A equals F over M. But one can also think she's probably drawing on chemical inspiration here. You can think of like hydrogen and oxygen atoms together creating a water molecule. So with this alternative definition of causation, Shepherd goes on to argue that an effect is something new only relative to the objects that caused it considered separately. So think of like an H2O molecule. It's new relative to hydrogen and oxygen atoms when considered apart from each other. However, the effect is equivalent to the union of those two objects which caused it. So she says the union of those two objects is the cause of and is one with the effect. End of quote. So this is very different from Hume's picture that cause and effect are separable. So again, think of a chemical example, like H2O is equivalent to the union of the atoms that caused it. For Shepard, that's why there's never a cause without an effect and an effect without a cause. They are but two different ways of looking at the same thing. And Shepard also saw this pattern, this causal pattern in mathematics. So think about how 12 is different from the numbers 7 and 5 considered apart from each other, but is equivalent to the combination 7 plus 5. There are two different ways of looking at the same thing. So then Shepard goes on to argue that if causation is two entities combining to create a third, they are synchronous, not successive in time. So I have here, she says, antecedency and subsequent, so like one thing being prior, following each other, are immaterial to the proper definition of cause and effect. So she thinks time doesn't have anything to do with causation. On the contrary, although an object, in order to act as a cause, must be being antecedently to such action, so like it has to exist before it acts as cause, but when it acts as a cause, its effects are synchronous with action. Effects must necessarily be in and with their causes in the very moment of the effect's formation. Another quote, she says, in their unions, like when these two or more objects combine, there exist those newly formed objects or masses of qualities called effects. For in this union, cause and effect are synchronous, and they are but different words for the same essence. And she gives examples of this, and one she gives is Newton's first law. For the proof of the simultaneous action of cause and effect, let the reader reflect that every object would remain as it existed at any given moment unless it were interfered with, and an interference cannot be either before or after itself, but must be in and with the same moment of the change occasioned by it. So here, think of like a collision between two billiard balls. While it occupies a small, finite interval of time, that collision, she thinks that during that brief time period, one billiard ball's momentum is decreasing continuously as the other billiard ball's momentum is increasing continuously. So they're synchronized. One can also think of gravitational interactions here. Like it's not as if the sun's force is exerted on the Earth and then the Earth keeps orbiting around the sun at a later time. Rather, these are synchronous occurrences.
3 minutes left.
Yeah. Okay, so maybe I'll just briefly mention this one part that's that I find a little puzzling. So I'd love to get what other people think about this. I'll end with this one. So one other striking feature of her view is that she thinks that there's some mutual interaction that happens in causal interactions. So she has a non-linear view of causal interactions. But it's not clear exactly what she means by this. So this is what she says. The manner of efficient cause is by mutual and simultaneous affections and interactions of particles or qualities. And she says, all qualities of existing objects play on each other as mutual cause and effect. I mean, she said there are two different ways one can read these quotes. Like, is she saying that every cause and effect mutually cause each other? Like, every cause is both an effect and a cause?
I can give some comments on that if you want to hear some things now, or we can discuss it afterwards.
I would love to hear. Or does she mean that the objects that compose the cause are mutually interacting? Yes, I'd love to hear what. So she sees some kind of reciprocity here, but yeah.
Let's maybe discuss it offline. And whoever is interested in discussing this philosophically, let's jump on the Discord at some point where we can all chat about it. Instead of doing it in this forum, I think for those that are philosophically inclined, it could lead to quite a long discussion. So let's rather maybe have it there.
We won't be able to have all those discussions now, We can, Sandra has 1 more minute, so I suggest let her use that up, and then we'll finish all the talks. And if, depending on how much time we have, then we can discuss everyone's together.
Yeah.
Okay. So Sandra, I mean, parting thoughts.
So that was just briefly. I mean, later I was going to talk about how she thinks about processes and what happens, but basically, very shortly, it's just she thinks that when you have temporally separate processes, there are just lots of these synchronous interactions added together in succession. Yeah, that was just what I was saying. So that's just very briefly, yeah, what her core account of causation is, or how I'm interpreting it, and how it contrasts from the dominant sequential linear view.
All right. My suggestion would be, Sandra, that certain points which you want people to comment on, reflect, think, as James just pointed out, at any time later in the day or so, put them on the relevant philosophy channel or so. And, you can really put it as provocative challenges for people to think and comment on. So that would be great. Thank you, Sandra. Let's go to Semi.
Hello.
Hello.
May I share my screen?
Sure, go ahead, please.
Okay. I think you see the
Yes, we
well.
see. Yeah.
Actually, this is my most interesting work, but it's already on the Wolfram community. You may check it out. It's about the Leibnizian interpretation of the hypergraphs in Wolfram model. Then it has very kind of material. But today I would like to talk about the concept of parabolic numbers. It's not some super important work, but I think it's kind of interesting. As you know, there's that complex number where I square is -1. Then, by the way, sorry, I couldn't prepare some presentation, so I'm just going over the PDF. Then there is the concept of p-complex numbers. These are defined similar to the complex numbers, but I square is equal to p. Here, p is a real number. If it is less than 0, the numbers are elliptic. They parameterize ellipses. I mean, in this form, the modulus square of the p-complex numbers equal to that one. So if p is less than 0, then this is kind of the elliptic equation. If p is greater than 0, these numbers parameterize hyperbola. If it is 0, then it's called the dual number. I published some kind of work on the idea that we may use these elliptic numbers to parameterize the elliptic trajectories in the Newtonian central force potential. After that, it was easy that it could be generalized to hyperbolic case, but I kept thinking about the parabolic case because this is quadratic in x and y, so it cannot parameterize parabola, whatever the value of p is. So this paper is the result of this kind of thinking. The idea to define parabolic numbers is to make this imaginary unit, which I call J at the moment, and will define it shortly. Then we need to make this J coordinate dependent. So in this case, where is it? Here. J square is equal to P, and P is a function of Y. And this is 1 over alpha absolute value Y for some alpha greater than 0. For this is the number I where its square is plus. So it's kind of the hyperbolic unit. Then we define the parabolic number Z in this form, in the kind of what we may call in hyperbolic representation. So I define kind of their addition. These are just done that. These are kind of the added values. Multiplication is also defined similarly. Complex conjugation is the same as in the other p-complex numbers. Then there is the distributive property of multiplication over addition. So they are kind of very nice numbers. Here I calculated the exponential of is it e to the z, where z is a parabolic number. What's interesting is that, for example, the complex numbers or the p-complex numbers are defined kind of on a flat surface. Even if you make p as a function of y by suitably changing coordinates, you may obtain this form, which is the metric for the hyperbolic numbers and also the two-dimensional Minkowski spacetime. But if, let me see, if p is a function of x and y, for example, in sine square x, then the manifold is non-flat. In this case, which scalar is equal to 2. Of course, it's another problem whether this function of p defines a kind of consistent number system. So yes, my motivation was that we need a kind of numbers system to parameterize this parabola, because that one, the last one that couldn't be parameterized using p-complex numbers. So with the publication of this work, we kind of obtained the set of numbers whose circles parameterizes conic sections kind of have been completed. Then I gave some kind of examples in the case of an electron under a constant electric field. So if it has a velocity component perpendicular to the electric field, the trajectory is a parabola. It's some simple idea. So I end the paper with kind of some thoughts. For example, in the parabolic number case, p was positive, but could its sign be changed in some different parts of the kind of the manifold? That would be an interesting question, because in this case we would not have some let's say the metric changes actually. So these are that. All right. So my presentation has been kind of very quick. I just wanted to give my main motivation, and that such numbers can be defined. So that's the takeaway message for that.
Okay, thank you. Let's go to Pavel.
I will stop sharing. All right.
Maybe I'll share just part of the screen. Wait a second. Windows here. Good. So my talk is going to be a little bit physical. So I try to, because I think that most of the people, there is more physicists than mathematicians. So basically this is going to be some mathematics very much formulated in the language of physics with physical motivation. So what I started doing during my PhD was basically a project starting with Chern-Simons theory. I mean, we did not know at that time that it was Chern-Simons theory, but it is Chern-Simons theory. Our Chern-Simons theory is given by this action, which contains the kinetic term, it's the first term, and the ternary interaction. Q is a smooth, closed, oriented manifold, and the field is a differential form on that manifold. So it can have also degrees. It can have also various degrees. What can you do with Chern-Simons theory? You can build a perturbative quantum field theory from that. What is a perturbative quantum field theory? It is basically a way. It is basically a recipe how to compute expectation values of your observables, which are functions on the space of fields, and you compute it as a path integral, which is some idea of Feynman and also probably previously people, but basically the idea is straightforward. You just take Taylor expansion of the integrand and you reduce everything to the case of a monomial times a Gaussian. Yeah? And you can then introduce Feynman graphs and Feynman rules to keep track of the integrals, and you arrive to so-called Feynman rules. And in this case, the Feynman rules which we considered were as follows. So we were associated to label directed trivalent because we are having ternary interaction, trivalent Raybon graphs. You associate an integral. Yeah? So here, what is new probably for if you have never dealt with ribbon graphs, then this is for you new. A ribbon graph is a graph which at every vertex has a given cyclic order of the neighboring edges. Yeah, so you know which vertex is first, which edge is first, which is second, which is third, relative to this vertex, which allows you, for instance, if you come along one, can you see my mouse cursor, or you cannot? Can you see my cursor, or you cannot? Probably cannot, right? Okay, good. But it allows you it.
Oh, we
okay.
can see your
So
cursor there now, but it's
Yeah,
just
now
a small.
now it's
yeah.
visible.
Okay, so it basically allows you to if you come to one vertex, it basically, for instance, from this side, and it allows you to say where you should go to. So you have to rotate, and we should go here, and here basically it is. Yeah, so basically this is probably not the correct direction. I'm now thinking what is now wrong with that. Yeah, so here and here. Yeah, so basically, yeah. But you can associate to such guys, you can associate integrals, which is probably clear from the picture how it is. And you have exterior vertices, and at the exterior vertices you input harmonic forms. Harmonic forms are special elements of the Dram complex which satisfy this equation, which is an equation of motion for this Chern-Simons functional. And P is a propagator, which is in this case the inverse of the Dram differential. This how you obtain this pxy in the integrals. This is just the integral kernel of this operator, which is in this case a form, which is an n-1 form on the product. And one can show that such integrals are always real, always exist. So there is no kind of like no problems with convergence. If the propagator satisfies certain regularity assumption on the diagonal, but this is too mathematical. Good. Maybe you noticed that I was talking about functions on Dram forms, but here I am not putting Dram forms. I am putting harmonic forms. So these integrals, these Feynman graphs, actually correspond to an effective theory on the harmonic forms, just for experts. And this we considered Q was any dimensional manifold, so a dimension n, but in 3 dimensions. This reduces to the BV BRST action of the U1 Chern-Simons theory for the one form. Yeah. So if you want to kind of gauge fix the standard Chern-Simons theory in 3 dimensions, then you have, for instance, the Fadeev-Popov method, or you have this BV method of gauge fixing, that you first extend the phase space so that you have more space, you add the ghosts, and then the gauge fixing is kind of more like natural process. Also, what you don't see coming from the functional are the signs. There is this ribbon structures and the signs in the 3 dimension. This is some relic because there is some framing anomaly of Chern-Simons theory, which people solve by adding some additional geometric data like framing, and this is the cause of this extra orientations. This analogy we just started with these Feynman rules, because they are also we started with these Feynman rules, and everybody is welcome actually to start with this action and try to really check that these Feynman rules are coming out from it. And except for the dimension 3, the origin of the signs and everything is also not that clear. This is an open question. Okay, but with these integrals in hands, you can kind of reinterpret these graphs, and you can, because you are having the cyclic orders at every vertex, yeah, then it allows you to actually thicken the ribbon graphs into oriented surfaces with boundaries. Yeah, So basically here you have this triple vertex. You can thicken it, and following this orientation, you are getting oriented boundary, which you will draw as a cup. And on the top of that, and on the surface of the cup, you are going to draw the original diagram, which basically leads you to such pictures where you are drawing oriented surfaces with genus and with boundary, and on these surfaces, into them you are embedding ribbon graphs, which are Feynman graphs. Actually, what you can show that with this view, these operations which you obtain by fixing exterior vertices, number of boundary components and genus, and summing over all isomorphism classes of ribbon graphs, they satisfy something called quantum A-infinity algebra, which is a generalization of a standard A-infinity algebra, where there are operations with higher genus. And this is something what is in physical literature called open string field theory. So it is an algebra which is governing open string field theory. And actually, due to cyclic symmetry at every boundary, you can view these operations as linear functionals on the you have L boundary components, and you can view it as a linear functional on the L tensor product of cyclic words. Okay? Imagining that to every boundary component you are feeding cyclic words, and you are summing over all possible isomorphism classes of the graphs and so on, and you obtain these maps by MLG. And having this, you can actually obtain also closed string field theory. I will now tell you how. So you start with certain canonical operation on this space of the cyclic tensors. For this, actually, I wrote recently, not actually recently, but I published recently this notebook, which actually implements that, the canonical structure. So you can check it out. You can play with that. And there are better pictures and better explanation. And basically, just with the product, we are having a product, we are having the integral. You can define canonical operations which take some cyclic word of this harmonic, which take two cyclic words of the harmonic forms and associate to it one by connecting each pair, by pairing each pair by the pairing in all possible ways. Similarly, you can define a coproduct just dually. Yeah? Actually, yesterday we realized with Carlos that they could be also written as perplex diagrams. Although, so at least the first one, the second one, we don't know how to represent by, or I don't know, maybe Carlos knows how to represent a coproduct by plex diagram. So, but at least the first one is just a plex diagram. And these operations actually satisfy involutive bi-Lie algebra. This is basically Lie algebra to co-Lie algebra, so the dual relations and some compatibility relations, which are schematically here. These pictures, you have to imagine that you permute everything in all possible ways. So it's not just one term, but you just have to permute everything in all possible way, and then you obtain the zero. So there are like 1, 2, 3, 4 equations. The last one is called involutivity. This is Lie bracket, Lie co-bracket, Drinfeld compatibility, and involutivity is the last one. And actually, if you view it like this on this cyclic words, then having this quantum infinity algebra is actually equivalent to the fact that this collection, this MLG of these operations, is a Maurer-Cartan element. Maurer-Cartan element is something like admissible deformation of the canonical ideal structure. Yeah? So basically, Chern-Simons theory is defining admissible deformation of this canonical ideal structure. So you can apply it, you can deform it. Application of the deformation looks like this. You are basically plugging it into all possible inputs and outputs. There's probably more figures, but I just listed the interesting ones, the ones with there's more ways you can do it, but I just listed those which are having at least one input, so that they are operations. And actually, it turns out this is deformed IBL infinity algebra, and these co-brackets, they satisfy something called quantum co-L infinity algebra, which is in the literature closed string field theory. Yeah? Then the question is, we started with Chern-Simons theory, applied some algebraic constructions on that, obtained something related to strings. It's algebraic construction, so is there some maybe geometric origin? How can we see that basically we are having some strings related to Chern-Simons theory? So the kind of the conjecture, or where we kind of think that it should go, is that the geometric origin is actually symplectic geometry of the cotangent bundle, concreted topological sigma model, which is a string theory, a topological string theory of, or you can view some generalization which contains also curves which have here this is a curve, this is a oriented surface. These circles are boundaries. They are having some mark points or punctures. Here is some genus downstairs. These crosses, they are internal punctures which are interpreted like closed string insertions, and the punctures at the boundary are interpreted as open string insertions. And it's a theory of maps to the cotangent bundle. And instantons of this theory, which are finite energy solutions of the classical equation of motion, they correspond to J holomorphic curves, which are heavily studied in the field of symplectic topology, because they give invariance of symplectic manifolds. And actually, so the thinking is that the degenerate part of the theory, which contains these surfaces with boundaries on the zero section on the manifold Q, and no interior punctures, is responsible for this Maurer-Cartan element. Why I'm saying degenerate? Because cotangent bundle is non-compact, and every kind of holomorphic function must have, every bounded holomorphic function must be constant. So kind of these are in the, if the equation is unperturbed, there cannot be any non-trivial solution of this, because every has to be constant. So that's why it's not so clear how to obtain something like this. But why, by building this, during building this theory, you are making a lot of choices, so you can build some perturbative framework where this is actually going to be bringing something. And the idea is
2 more minutes.
And the idea is that this Maurer-Cartan element, this from the Chen-Simons tree on the left, that you can construct it also in the symplectic world by basically pulling back the forms to the moduli space, so to the space of all the solutions, or this degenerate solution integrating over. And there is this conjecture, which I would be very interested in, but it probably will take some years to formulate, to prove the things, that this Maurer-Cartan element from Chen-Simons theory and the one from symplectic geometry, if it exists, are gauge equivalent Maurer-Cartan elements for the canonical IBL algebra. So this would kind of connect Chen-Simons theory to symplectic geometry in this way. And then let me just last comment. What is this closed string field theory good for? The homotopy type of the deformed IBL infinity algebra is a smooth-oriented homotopy invariant of the manifold and corresponds, if Q is simply connected, to a chain model of the canonical topological string operations. So if you have a string, you can join them at the common intersection. On one string, if it self-intersects, you can disjoin it. And from this idea, the kind of the maximal what you can cook is basically some homotopy, some homotopy algebra on the chain level. This is some kind of refinement of the homology structure which was well known since like Chas Sullivan work on that string topology. Yeah, so thank you for attention.
Thank you. If you can unshare. All right, thanks. We'll come to discussions for everyone towards the end. Next is on my screen is Reza. So Reza, go ahead.
Hi everybody. I'm gonna share my screen to talk about the things that I found interesting. Actually, not during the past year, but during the couple of months. Actually, I was involved in some. Can you see my screen?
Yeah, now we do.
Okay. I was involved in some projects, but our last project, we found something interesting to me actually, and it's in the referee's hand, but I got this diagram from it. It comes from some calculations, which I actually did by Mathematica, but I'm going to first talk about what this diagram tells us, and then I'm going to let you know that there's something that caught my interest recently that I'm going to study and gain more insight on. So in one of our recent works here, we studied the probability of a neutrino becomes right-handed. A left-handed neutrino becomes right-handed. As we know, neutrinos are born left-handed, and our detectors only respond to left-handed neutrinos. So if somebody would just suggest that right-handed neutrinos are hot dark matter because we can't detect them, they're massive, so they do not interact with us. So maybe they are a candidate of dark matter. So in our study, we assumed that neutrinos are moving in curved spacetime, and because of that, they precess and they can change their helicity. So for our spacetime, actually we studied some spacetimes, but the most interesting one to me was the interior Schwarzschild spacetime, which roughly gives us the Earth. We can model the Earth by solving Tolman-Oppenheimer-Volkoff equations in general relativity, by assuming that the outside geometry is given by the Schwarzschild and the interior metric, and what we find for interior actually gives us a solution to a planet or a star or anything. This is not a good approximation because we consider in that it can be found in every general textbook in general relativity. The simplest case is when we assume that the density inside the planet is constant, which is not a good approximation, but it is roughly, it's not that bad. So the situation is that a neutrino enters here, and this is the center of Earth, and this is the closest distance to the center of the Earth. So it enters here and we detect it here. So we wanted to know what is the probability to change for this neutrino to change its velocity, to become from left-handed to right-handed, to evade actually our detection. So we did it with some calculations and numerical computations. We end up with this graph, which again, I generated it by Mathematica, but I just took a screenshot because I didn't have time to show you the codes. But anyway, it tells us that, this axis tells us the probability, and this axis tells us the impact, the closest distance. So we found the probability with respect to the closest distance to Earth. So if B is 0, the neutrino just enters here and just passes through the center of the Earth and just we get nothing. The probability is 0. But for some value of the closest distance, the probability can go, can be high. It can be even 1. So at this, I think it was close to 100 of the Schwarzschild radius, 100 times of Schwarzschild radius, that all the the probability is 1, so all the left-handed neutrinos become right-handed, so we don't detect them at all. And it was really fascinating to me. Actually, our model is simple, but the result was really interesting to me. So that's why I'm going to I decided to talk about it here. And it's even more interesting because this is for high-energy neutrinos. So we expect that if high-energy neutrinos don't care about some gravitational field. It's expected that low energy ones just the same way that we study problems in scattering stuff, that when energy is too high, we expect that we don't see any effect. The neutrinos don't see the Earth at all, but in the contrary, even for high energy ones, we can see that the gravity, the gravitational field of the Earth can affect the helicity of the neutrino that much. That was for the first one. The other one I got interested in quantum chaos, and I started reading a book in that subject. I found it really interesting. I have no background, but I'm in the first chapters. But anyway, the concept of chaos caught my interest too much, but I've never had a chance to study it so far. But I just wrote this close to see the effect of chaos, and this is something that people call logistic map. And this is the first thing that you can see chaos, chaotic behavior. When you change your initial condition slightly, the dynamic of the system just change too much. So I just have this map, and I got the dynamic of for two different initial values. And this is, for example, the blue dots are for some initial values, and the red ones are for something different, but very close to the previous one. And we can see this is R, actually. This is a very, very bad plot, so I didn't specify any axis. But for different values, no, sorry, for the same R, but for different initial conditions, we can see that as R changes, up to some point, the system is not chaotic. There are some blue points behind these red points that you can see. But after some specific values of R, you can see the chaotic behavior, because by just changing the initial value, you can see that the evolution of the system can be different, because the blue dots and red dots are not identical. The red dot doesn't cover the blue dots completely. So that's the other thing that caught my interest, and I'm going to study to gain some idea. And I think that it will be interesting when you study chaos in quantum mechanics. I don't have any solid background yet, but I just wanted to share my interest with you. Thank you.
Thank you. If you can unshare.
Yeah, I'm okay. Stop share. Oops, sorry. Yeah.
All right, thanks. Let's move on and go to Jacopo.
Yeah, so let me share the screen. Can you see my screen?
Yes.
Okay. So I was thinking of talking about what I finished working on in September, which was my MSci dissertation, so my master dissertation. Sorry, just to keep track of the time. Okay, so basically this all started as a work to try and generalizing what is known as the Dirac quantization condition to gravity, although it turned out that, well, basically I decided to first start thinking about, instead of gravity, other non-abelian gauge theories that could be simpler to treat, so like Yang-Mills theories, etc., which are in a more layman term is like multiple copies of electromagnetism, but they're also self-interacting, because basically the strong force, for example. And so the Dirac quantization condition is a very interesting argument that was proposed by Dirac in 1933. I was here somewhere. And it's basically, it posits that if you have some electric charge and it's moving around in some loop, in some path, and there's a magnetic charge somewhere in the universe, then quantum mechanically the phase that is induced in the wave function of the electric charge through this path has to be I mean, for the theory to be consistent, this phase shouldn't exist, which means that if there's even a single magnetic charge, then the electric charge should be quantized, because if the charge is not quantized, then this quantity in the exponential is not one, so the phase is not one, and And so we have this condition that the product of the electric and magnetic charge are related by some quantity that is an integer multiplied by some normalization that depends on pi and h bar. And this was the first argument on quantization of electric charge, because before it was only known experimentally, and there was no argument for why that was the case. And although later on Dirac became a bit disillusioned on whether it would actually be a valid reason. I think just before in the 70s, to Hooft and Polyakov actually showed that you can get magnetic monopoles from some structures in Yang-Mills theories, and so that kind of sparked more interest. But this is not the topic of what I investigated, which was the problem of generalizing this to non-abelian theories, so theories where the gauge group, which is essentially the internal state of the internal the space of internal symmetry transformations that the wave function of the particle can have, is not a commutative group, so it has a more complicated structure. And this was mostly focused, I guess, an investigation in the first stages on the meaning of charge, because I thought charge quantum mechanical, like, no, charge in like, since charge is central to this, like what is magnetic charge, then it's important to first understand what was the what charge is, what the electric and magnetic charge in an abelian theory are. And before even that, just the word charge itself, because the difference between electric and magnetic comes when you have a theory like electromagnetism. But charge itself is a more general concept, which is related to conservation laws. And it is learned first in undergraduate physics as a result of Noether's theorem, which is when there's a continuous symmetry, there's a conserved current. But this is also reflected, and this can also be expressed in Hamiltonian mechanics, which then is a great way to generalize this to quantum mechanics, where any operator will obey some sort of conservation equation, where the operator, if the operator commutes with the Hamiltonian, then it doesn't change in time. And this is sort of becomes related to the ideas of representation theory, which is that essentially one can find representation for these these transformations in the groups, these symmetry transformations in practice. And basically the charges in a quantum mechanical system turn out to be exactly the kind of operators that generate infinitesimal symmetry transformations, which are called the generators of the group. And for abelian symmetries, this is relatively straightforward. It becomes more interesting for something like SU2, which is the group of spin, for example. And this is in fact, so what you get is that if you're building you're considering a quantum mechanical system, you will have that you have you have three directions of space, and you can measure the spin in those three directions, and those actually correspond to your three generators of this SU2 group, but they do not commute. It's a non-abelian algebra, and so quantum mechanically one cannot find simultaneous eigenvalues of these operators, which means that one cannot find an eigenstate that has well-defined values of these three charges. So, but what one can do is define these operators, which are non-Hermitian, so they don't correspond to observables, and can actually use them to construct raising and lowering operators that allow you to get states of higher charge from states of lower charge. And so one can actually observe that the charge itself, like there's only one charge here, and it is actually the value of in this case of spin, it's the spin. That's the charge that can be physically measured. And one could measure the spin in the z direction, for example. One could measure it in the y direction, but then it's a different eigenvalues, and this is well known, let's say, undergraduate physics. But what's interesting is that the same thing can happen for more complicated non-abelian theories. For example, this is a diagram that represents what happens for SU3. SU3 has actually there are two for SU3. There are two operators that, so it has 8 generators, but among these 8, you can find a set of 2 that do commute. And so here we don't actually have a single eigenvalue, we have 2 eigenvalues, and we represent these in a 2-dimensional plot. These are what in representation theory are called the weights of the algebra. And so the charges, these mu1 and mu2. And so the charges can lie, in this case of SU3, they're represented in this way. And the charges can lie anywhere in this lattice. One can make a similar construction as before, just using the property that the commutation with one of the, where did I find the commutation, if one chooses the right basis, which is called a wild basis to get this diagram, one can, by using just this property, construct same kind of ladder operators, but now which correspond to the addition of one of these roots to any and allow one to move around in this graph, in this lattice. And so it turns out that one can understand charges as vectors in these spaces. And this does allow, for example, this also sort of answers the question of why there are, which is a perplexity I had, of why there are sort of 3 quark charges like red, green, and blue. But actually the full picture is that there are 3 quark charges which correspond to the weights of the fundamental representation, but there's also 3 anti-quark charges or anti-charges, which are the ones of the anti-fundamental representation. And then but then the generators of the group are 8. So like why do we have 3 charges but 8 but at the same time there's 8 generators which are supposed to be the charges? Well, they can't all have simultaneous eigenvalues. You can only have 2. So charges can only be described as elements inside of these of this 2-dimensional space. Of course, one could make a change of basis and consider linear combinations of these, but at one time one can only consider 2 simultaneous eigenvalues. And this also shows how one can get quarks just by adding up a charge and an anti-charge. These are the charges that the quarks would have in a SU3 color theory. And this sort of, once one defines the right kind of product that one can have about among these vectors in this space, which are these charges, then it's possible to generalize the condition. In fact, the condition is the same once one can define this product. And it turns out that if we take the electric charges to be sitting in these weight lattices, the magnetic charges will actually be elements of this form, which are called co-roots. And this is due to this property. So if this is our electric charge, our magnetic charge, and our magnetic charge has this form, the product will be an integer value.
But
And
2 more
so-
minutes.
Yeah.
Yeah.
And
2 more
so,
minutes.
yeah. And so it turns out that if one consider these co-roots, so the magnetic charges to be sitting as co-roots in these spaces, then one can have similar quantization condition. And this doesn't have to be taken as if there's a single magnetic charge, then the electric charge is quantized. It can also be taken as a compatibility condition between electric and magnetic charge. One could only have electric charge and then it can be continuous or whatever. But if one could have discrete electric charge and not have magnetic charges. But if there is a magnetic charge, then they have to have this relationship. So this is a very sort of abstract kind of statement, which is, I guess, the kind of statement that one often gets from group theory. And yeah, I would say that's enough. And if you have more questions, I'm happy to talk about later.
All right. Thank you. Great. So then I have Shraddha. Shraddha, go ahead.
Okay, I have some slides made, so I'll just share those.
Perfect.
Okay. Okay, so I might finish before 15 minutes. So I will appreciate any questions if you have. Please just stop me in the middle. And I work in experiments, so it's slightly different from what most people work on. So really, if you have any questions, just yell at me. Okay, so what I worked on was Hamiltonian, during my PhD, was Hamiltonian engineering using synthetic dimensions of an ultra-cold atomic gas. So as I will show later, Hamiltonian engineering means that we can basically construct or really engineer and implement any Hamiltonian in 1D, like a tight binding Hamiltonian, using our experiment. And so this is like a typical picture of my setup. These experiments tend to be pretty expensive. And so it's a whole zoo of optics and vacuum chambers and such. And so the actual action that happens is in a vacuum chamber that looks like this. It's an ultra high vacuum chamber, about 10 to the minus 12 torr. So about 10 to the 12 below the sea level pressure. And we basically direct different light, magnetic fields using the optics and these wires that you see around. Okay. So just for a very big picture view, what are ultra-cold atoms or Bose-Einstein condensates? So if you are in the northern hemisphere, then it's probably very, very cold. So the coldest temperatures on the planet, I think, are minus 70 C, if I'm not wrong, maybe even lower than that. So if you think you're cold now, then you'd be really cold inside the vacuum chamber in my lab. And because what we do is cool down atoms to about 100 nanokelvin or so. And here, what you see is a video of different images. And the video is composed of images that is taken of a gas that's expanding. And we take the image after it expanding for a fixed amount of time. So, and with time, we are cooling the gas down more and more. And so you see that it expands less and less because it's way colder. And the final image that you see is uh, a Bose-Einstein condensate. And this is a picture that we take with our camera in the lab. And this is about 12 or 15 microns in the length. So that's like a typical length scale. So really, for perspective, if you had a thermometer from the Earth to the Moon, where Earth was absolute zero and Moon was room temperature, then the temperature of this gas would really be just or the mercury level on the temperature would just be a width of the hair away from the absolute zero. That's how cold these gases are. And one really cool thing is that now Bose-Einstein condensate, so it's like a big macroscopic quantum mechanical object. So just like light diffracts in typical Young's double slit experiments, here these atoms also diffract from light, and they split into different orders, just like light does. So just to say that BC is quantum mechanical object, and these atoms have a wave nature now, and that's readily seen in the lab. So why should we care about this at all? So Hamiltonian engineering is really useful in exploring new phenomena like supersolidity is a recent big result, or analog quantum simulation. People also use Hamiltonian engineering for quantum metrology, like sensing, making really good sensors to sense electric fields, magnetic fields, gravitational fields, and also the hype these days, which is quantum computing. And typically, people use things like optical lattices, which is an interference pattern made by light, and the atoms occupy the minima of that interference pattern. People also use interactions between atoms. Um, this is slightly technical, but people also use Floquet engineering. So they move these optical lattices around periodically to realize certain Hamiltonians. And what I use is synthetic dimensions, which I'm going to explain later on. And so we basically use the synthetic dimensions of these ultra cold atoms, and we use optical lattices to make different Hamiltonians. So this is a typical schematic of the experiment. So once we have the Bose-Einstein condensate, which is basically for all practical purposes, a really cold gas of atoms with a very narrow velocity distribution centered around zero, including the interaction effects and the trap effects, you could think of the atoms having a free particle dispersion relation. So it's a parabola. And so now we have, or I guess I aligned some laser fields on so that they hit this Bose-Einstein condensate. And what happens is a absorption emission process. And when I turn these two laser beams on, the atoms get a kick, and they get a kick of 2h bar k, where k is the wave number of uh, these two these two lasers, and the atoms start moving with 2h bar k. Now, if you keep adding many more lasers like this, they will get different momentum of 2h bar k, 4h bar k, minus 2h bar k, minus 4h bar k. And in this sense, so we are calling these momentum states the synthetic dimension of the atoms, and we are using these quantized momentum states to make ladders of momentum states. So these are quantized in 2H bar k, and that is why we call it a lattice. And the very important bit, probably the take-home message of this entire presentation is that in some limit, this entire experiment actually maps onto a 1D tight binding Hamiltonian. And with the frequency and the phases of and the amount of light that we throw in each of these laser beams, we can basically control each and every term of this tight binding model, where, this is the site energy. We can control that. We can control the tunneling strength from one side to the other of the lattice. We can also control the phases very, very well, also for each lattice side. So in this way, this is a highly controlled, very, very precise system. And the reason why I said that this is important for quantum simulation is that we can use this ultra cold system to mimic things that happen in different condensed matter systems, because a lot of um systems in condensed matter solid state physics can be modeled by a tight binding Hamiltonian. So this is the technical bit about the experiment. Finally, a last bit to show you about the typical experiment. So the typical experiment just works like this. There is a Bose-Einstein condensate, and we turn these lattice beams on, and then it goes on, undergoes some evolution based on whatever Hamiltonian we have turned on. And after we are happy with the evolution time, we turn off these lattice beams and let the atoms fall, and then we take an image that typically looks like this. And in this way, our measurement is that we figure out how many atoms do we have at each lattice site, and from that we figure out, okay, what would have happened during the evolution process. So I think that's it for me. Thank you.
Thank you. All right. Anyone else? I think we've covered everyone. Great. Then let's actually go to the discussion. Now we have sufficient time. We could go in order, in matter of fact. So let's start with Sandra. There were a bunch of comments, questions, and suggestions about Sandra. So just speak up, anyone, whoever has something to say.
Actually, I had a question for Sandra.
Go ahead.
So, in Lady Shepherd's view, then what is time if cause and effect are the differentiation between cause and effect is meaningless? Then, yeah, what is the view of time in this thought?
So, so she basically thinks that when you have processes or things that take time, she's saying if you zoom in on those processes, they're composed of like individually synchronous interactions. So she thinks that the passage of time is the succession of lots of causal interactions, one after another. But other than that, she didn't. She wrote very little, so she didn't expand on a whole theory of time. But yeah, that's yeah.
In other words, it seems she's giving precedence to causal relations rather than continuous time as we know it.
Yeah, exactly. For her, causations is fundamental. It's like a part of the building block of nature, and Thanks for the
That,
question.
And yeah, go ahead,
Yeah,
James.
I was just going to say that this kind of makes a lot of sense in our formulation of causal graphs and events and all that kind of stuff. It kind of fits in quite nicely with our models.
Yeah. One question I had, if she said, as you mentioned, she says that the way she describes cause effect is very close to composition. Is there some clear distinction of what composition should mean and this notion of causation should mean in this picture? Or so is it identical? And if it's not identical, what precisely is the difference?
Do you mean what the difference between composition and causation is?
Yes, from
Okay.
causation in Shepard's view, yeah.
Yeah, so again, it's hard to, because Shepard wrote so little and it's very fragmented, so one has to like speculate a lot and fill in gaps. But the impression I get is I think she thinks all causation is composition, but not all composition is probably causation. So, yeah, because there's lots of things.
Do you have some nice example of a composition that is not causation?
I don't take a simple like like a because for her, like, causation is when something changes or when something happens, and we try to explain what caused that change. So I suppose anything that isn't change. So I don't know, like a table is composed of these parts and things, but I don't know if she'd say they cause. But I suppose when you put the table together, they cause. But yeah, what were you? Did you
I mean,
have?
at the conceptual level, not at the physical level, there is something new. You had the legs and you had the base, and now you have the table. It's a new concept compared to the legs and base. So there is something new.
So if you go to like when the table was formed, yeah, so I suppose that is a good question. Like, can there be compositions that aren't causal? Or I don't know. Do you think there are cases of when things compose others but they're not causal?
I was going to, just inspired from your talk, I was going to say there isn't any difference, because in any scenario, there are various levels at which you look at it. One may look at it at a physical level, one may look at it at a conceptual level. At some level, you'll always find something new, the most basic being the conceptual level. When you put parts together, the whole is conceptually almost always a little more than just the sum of its parts. And then maybe someone could say, okay, maybe perhaps even physically you could quantify it in terms of information or something like that. But it almost always looks like in any setup, one may be able to think about it this way, that the composition never remains a process in which something new hasn't come out. But it's something to think about. I mean, I didn't because you mentioned, I wanted to understand, as you said, that Shepard perhaps hasn't specified all of those nuances. It is other people like yourself and others who study that work who try to interpret and make sense of what it may be. But if you do have some thoughts on this in the coming days or so, do kind of weigh in, because composition is very important for not only the stuff we do in the physics project, but even generally. I mean, in the sense you can think of it this way, the whole of mathematics is built on various notions of compositionality. It's a very, very, very central concept in the mathematical and the physical sciences.
Really interesting. Yeah, I think you're really onto something. That what's unique about Shepard's view is that causation is composition.
And that itself would be a sort of startling and interesting statement. If it is the same, that itself has a lot of insights to reveal.
Thank you.
Okay.
That's really helpful.
Yeah. Anyone else wants to ask about anything related to Sandra's talk?
Yeah, Sandra, I did a huge brain dump on the physics channel. So, at some point, if you wanted to scan through that. But this concept of composition, similar to how I think about it, where it's basically just relationships. So when you boil down to even the physics project, like relationship could be the point at which edges come into a node. and that is what exists most fundamentally at like the basis of reality. And it's the arrangement, interaction, and changing of those relationships, compositions, cause and effects, whatever you want to call it, that kind of can be a model to describe everything.
Yeah. And in fact, in the same way as in our physics project, this again coming back, because this notion of compositionality or composition slash causation as we view it is so central, even time as we know it, continuous time, is thought of as something that emerges rather than is already put in. And that's what we do with our rewrite rules. We literally don't have a global notion of time. We just have some local computations. And then for time, the observer is necessary, and it's the existence of the observer that then kind of imposes some notion of time. So
yeah,
okay.
It's like the observer is what creates the constraints, because at the limit, the Reuliad is all possible rules applied anywhere all the time. So the only constraint in such an object is where you place the computationally bounded observer, and that limitation is what helps build these ideas of like how time can then emerge, entropy, and a whole bunch of interesting things kind of fall out from that basic structure.
Indeed. Okay, great. All right, let's go to Semi. Questions for Semi Stock? So then let me start, as people are thinking about it. There's one thing that came to my mind. I would have. So the kind of, as you were explaining, I was wondering that how should I understand whether these numbers, you can take any of them, maybe the parabolic or the elliptic. Sure, I mean, from the definition, it was clear that they seem to be something new, but how do I know that they are genuinely new in a fundamental sense, or there may be some theorem which says that for any of these, say, parabolic numbers, you can always find a map to the complex numbers, and then whatever theorems you're proving about these parabolic numbers, you could just as well prove in the complex numbers. And in a way, these parabolic numbers are just another way of putting together complex numbers, meaning that they are not fundamentally new in the way that complex numbers are fundamentally new compared to real numbers, but they are just sort of things that you could factorize and you just get complex numbers. How do I know that is not the case?
Actually, you can map the parabolic numbers to hyperbolic numbers where I square is 1. So in a way, what you say is kind of correct, but the thing is that to have an explicit kind of representation of numbers that parameterize parabolas. So that was the main point. But as you said, and actually I included at the end of the paper, there's a one-to-one map between parabolic to hyperbolic, and you can map hyperbolic to complex. So in a way, they are kind of closely knitted family of numbers.
Okay. Or what may happen is that if you really want to dig deep into finding where, in which scenario they are really irreplaceable by any other number system, you may have to go on some particular type of geometry which coordinatize these numbers in such a special way that nothing else would really give a kind of a kind of well-defined mapping. Everything else might have some singularities or might have double covers or something, and there may be certain geometries on which this is the perfect mapping. It could be that if you take some solutions of PDEs or ODEs on certain geometries which are like parabolic or some things like this, this may be the solution and there may be nothing else, and everything else becomes a little bit patchwork sort of. It may be that. I mean, but other than that, if you just give me these numbers generally and don't put any geometric constraints, nothing, it would seem to me like, unlike the quaternions or the octonions or the complex numbers, these are not of those kind of classes which you couldn't express from one to the other.
Actually, the case you mentioned actually is a very important case, and actually, it may be in action if we define the square of the imaginary number not as a function of y, but also as a function of x. So in that manifold, there may be kind of non-trivial curvature. So what you're referring to, yes, maybe in that case,
Yeah. Yeah, so the way I'm thinking it is that they may be coordinate charts on some very specific geometries. And then that's what then that is the real meaning of these numbers, as opposed to, I mean, these numbers may be totally useless if you just see them on the flat plane or the complex plane. They may just be trivially factorizable and serve no purpose. But on these very particular geometries, they may for which you may actually be able to solve, I don't think it'll be infinitely many. You may be able to write down a master equation, like a master differential equation, and say that the solutions of these are the coordinates are coordinatized by these numbers, or in other words, these numbers are the coordinate solutions of that particular class of differential equations, and that's what its actual geometric significance may be.
Yes.
So that may be an interesting exercise, actually. Okay.
Yes,
Any other questions for Semi? Okay. So before we move on, Semi, I mean, this is it's an interesting enough system still. Feel free to write a community post on it in future. There are lots of people in the Wolfram orbit who have a inkling towards all sorts of combinatoric and geometric properties of numbers and other things. So it would still make a good community post if you want to think about it. Let's go to Pavel. All right, maybe I'll just start, and then others, please just join in. They were really exciting talks, so there are lots of things I would like to ask too. I mean, the way you showed everything, it was tempting to ask, how do you write down the duality between the open string picture and the closed string picture? Meaning just the duality in terms of those diagrams. Those, I think, people have, topologists have studied them. How would you do that? And how would you express those? And if you do, I mean, this would be a great thing to just express in terms of our Plex diagrams, because our whole Plex diagram business, as you've seen in some of the recent work with Carlos, was in terms of some of these higher arity operators and algebras rather than the Bailey algebras you discussed. But if you know how the duality works at the diagrammatic level, we might be able to implement it in our using the tools we have kind of been thinking about.
Wait, what do you mean now precisely by duality? Because the way it was that there were some canonical operations on the cyclic words, and these were representing some sort of canonical closed string field theory. I mean, in the language, the correct language is the involutive Billy algebra, and then there is this quantum infinity, this Maurer-Cartan element, which is Maurer-Cartan element from this involutive Billy algebra. And what do you mean now by the?
I mean at the level of the Feynman diagrams, the closed string diagrams and the open string diagrams, meaning literally the scattering amplitudes.
Yeah, it would be actually. It's like you mean like that connecting the things together, or.
So for example, let's take a simple open string diagram, which is just like a three vertex with three strips on these three strips, right? So you have three boundary conditions. You can topologically deform this into a disk with three punctures.
Yeah.
Okay, so you can so for example, from now this disk with three punctures. How would you make this into a closed string diagram? Let's see. Well, to make it into a closed string diagram, I would probably have to do a little more. If these punctures were even identified, then you may convert this open string diagram into a closed string diagram by shrinking the holes and making it like a sphere or a torus with punctures. You see,
but then you would be shrinking all the punctures at the boundaries. Would be shrinking to one. Okay, I see what you mean. Okay.
So maybe I gave the wrong picture. You can start with the sphere with some n punctures, and by itself it's a closed string diagram. But now you open the punctures, and those are Wilson loops. And now you're just following the ribbons, and that's your open string diagram.
I think I need to write it down.
And this dictionary, you know, people have then even related it at the since it's an amplitude actually of the topological theory, people have then even expressed it in terms of the actual algebraic transformations.
So is this something what already has a name, this kind of duality what you are talking about?
I've seen some papers and talks. I don't know. I think that they usually, at least in the physics language, they just call it open-closed duality. And this has manifest in various theories. I mean, it depends on the topological field theory you're working with. I've seen it at the level of topological string theory. I've seen it. I think it has also come up in the level sometimes. So in topological string theory, if I'm not too away from what they were discussing, it may have something to do with A and B model also. And then people have also discussed it in the context of matrix models, but that I'm less familiar. There is a paper of some author from Chicago a few years ago. If I can find it, I'll just post it to you on the Discord.
Okay, thank you very much. I heard it, but I did not know what it was. And actually, just looking at the pictures, it looks similar. I'm now on this NCAT and category lab. There's also a page about it. So this might be actually related. I will check it out.
And the other thing I wanted to ask is that when you were trying to show the processes of the IBL algebra, you of course you had those that identity with 5 or 6 terms equal to 0, and you mentioned each denoting something. But I would have thought that all of those are just the Frobenius algebra. Like literally, whatever you do with the components of a Riemann surface, the pair of pans, the caps, the cylinders, that's just Frobenius algebra. So by putting Frobenius algebra, I mean, yes, you could build other algebras, but at the base of it, it's just a Frobenius algebra, right?
Wait, isn't Frobenius algebra? So Frobenius algebra is some kind of bialgebra, right? Or is it?
Yes, it is a co-algebra in the sense that you have a product and you have a co-product. Indeed. So in that sense, it's a bialgebra. So
I think this has different axioms, different compatibility conditions of the bracket and co-bracket than the Lie bialgebra and different symmetries, right? Frobenius algebra is probably associative, and this is Lie algebra, isn't it? Or
yes. Okay. So I just wanted to understand what's the main difference. Okay.
Yeah. So this is really Lie bracket, Lie co-bracket, and the compatibility is the Drinfeld compatibility, which can be also formulated probably in some kind of that something is derivative of the other or something like that.
And it's a Lie bracket, meaning a binary Lie bracket or a higher
binary Lie bracket. It's normally binary Lie bracket and a binary co-bracket, and they have to be compatible together.
Okay. Great. This was really nice. I mean, for all of you, feel free, depending on what you want, to put those slides on the Discord, because whatever you presented was just great stuff to listen to. Go ahead.
This field is still kind of open, because a lot of this stuff it's very hard to approach. I was also missing when I was working on that. There is a lot of signs, and the sign computations are kind of heavy, and it was I also used Mathematica actually to check some computations, for instance, for this canonical Lie bialgebra. But basically, all these things which I was saying today is I think everything is. I mean, there are things proven. For instance, there is proven that the Chern-Simons Maurer-Cartan element is well defined. That it's independent up to gauge equivalence on the choice of the propagator, and so it is related to string topology. I did some computations. There is some algebraic approach in simply connected case and so on. But these connections to physics and to symplectic geometries is nowhere written yet. And so this can be still kind of like actively basically investigated. Yeah. Also the analogies of our action with the Chern-Simons action, because many times people are confused. What kind of action are we actually using? What kind of graphs are there? Why are there designs and everything? So this is all kind of can be still investigated.
So when you were discussing the symplectic geometry part, I was not sure whether you meant that was part of the open string field theory, the closed string field theory, or it could be either.
No, actually, if you consider like the theory of this is open closed the open-closed theory. So I had the Riemannian surface with both punctures on the boundaries and punctures on the interior. So we're having both closed strings and also open strings. And for this, and the correct boundary conditions are that the boundaries have to lie in for these holomorphic curves, the boundaries have to lie in Lagrangians, which is the zero section in this case. So basically, then the picture look like this: that if you don't have any interior puncture, you are just end up. That's also the original reason why I was drawing it upside down, so that it's kind of this cap. But this is something what I ask kind of it's counting this. So basically, what is the problem there? You are studying spaces of solutions of this holomorphic equation to set it up properly. These spaces sometimes are not smooth manifolds. You have to perturb something so that they are transversely cut. So there is a lot of kind of choices, and people don't know really how to count, for instance, with higher genus. So with higher genus, there are still some transversality problem and everything. So it's hard to write it down. And but what I was actually thinking related to this holomorphic curves, there is this process of holomorphic curve breaking, because if you have a sequence of holomorphic curve which is not convergent to another holomorphic curve, the only thing actually what can happen if it is finite energy is that it breaks into other holomorphic curves. Yeah, which is breaking is also some kind of process. It can break at various places, and basically the origin of all this structure coming out, all these algebraic relations, is some structure of the compactification of the moduli space of the holomorphic curves, which is based on the way how the curves are actually breaking. Yeah, so there can be like Koray-Mengen strata and higher Koray-Mengen strata, and the higher Koray-Mengen strata, they can be also approached by multiple ways from various lower Koray-Mengen strata, which is also kind of suggesting some kind of like graph or whatever, or there is always some algebraic representation of holomorphic buildings or something like this. One can write it down, but maybe there is also some graph description of like the boundary structure of this breaking of holomorphic curves or whatever. Maybe who knows.
It definitely looks like this breaking is related to some kind of geometric transformation itself. I mean, it could be there are some instances in topological string theory where some geometric transitions are probed in terms of how the strings on top of that geometry then behave, and there is there is a direct relation to, they sometimes call it just geometric engineering or something like that. Okay, great. Any other questions for Pavel? If not, let's go to Reza. Questions for Reza? So I think maybe there's one thing you may clarify, Reza, for everyone's benefit. You know, because when we have learned particle physics from our regular textbook course, neutrinos are meant to be left-handed because we think that, well, they are Dirac particles, not Majorana particles, and so we don't have right-handed neutrinos in our standard model, textbook standard model. And now you're saying that, yes, there may be a way to produce right-handed neutrinos. Of course, you're saying that they are not fundamental, they're just transforming from left. But give some way to understand how they are these things that we thought were not allowed, but somehow they could come up from some kind of helicity flip of the existing particles.
So they were born left-handed. So in principle, we can't just generate, we can't have any left-handed, right-handed neutrinos in a beta decay experiment. But we define the helicity, something like the direction of the spin, somehow when you compare the direction of the spin and the momentum.
Okay,
so
you just to be clear, you are being careful about the difference between helicity and chirality, right? In massless particles, there is no confusion, but in massive particles, there is. So you're just saying that they are right-handed in helicity. You're not claiming that they are right-handed in chirality. Is that correct?
No, they're left-handed helicity. They change the helicity, not the chirality.
So the chirality is always left-handed.
Yeah.
Okay, fine. So then they are not Majorana particles. They are still the standard Dirac particles.
Standard Dirac particles.
Fine.
Yeah.
Okay, fine. So that helps.
Yeah, and in general relativity, when something happens in like thermal precision, when the particle goes around a loop, maybe its spin just presets. So moving in a gravitational field, the spin of the particle presets to just become along the momentum, and so it becomes right-handed.
I see.
Yeah.
Anyone wants to ask something to Reza?
Yeah.
Go ahead.
So you had shown a graph where you were calculating the probability from going to a left to a right neutrino, and it went up and then went down.
Yeah.
Maybe I missed this, but is there any intuition for why it goes up and then goes down?
Actually,
Parameter?
yeah, at first it was a very weird diagram for us. So we tried to somehow explain it because our calculations, we checked our calculations tons of time, and all of them were correct. But you know, because it's a probability, we compute the probability with quantum field theory. So actually, it can be somehow, you know, if it goes up and up and up to tend to some value, it could be explained very easily because, for example, it's now far away from the center of the mass, and now it's a weaker gravitational field and blah blah. But really, we couldn't end up with something that actually convinced ourselves to why this happens, why this goes up for some specific values and then goes down. No, actually, I don't have any you know, any good answer to that question. At some point, I was just thinking, okay, just our relation says that, so we should accept that. But no, apart from that, sorry, it was something that I really thought about, but I couldn't end up with something.
But the going down means that the helicity is reflipping to its original state, right?
No, it means that the left-handed neutrino stays left-handed.
Yeah, so it flipped to right, and again it came to back left again, right? That's what you're saying.
Maybe that happens, yeah.
Because what I'm asking is if this flip is not stable, meaning that, you know, like it's not like a bistable dynamical system. You flip and it stays there. It flips, but it's metastable, so it reflips. It goes back.
Yeah,
And then if that's the case, because you know what you said, that at the peak is where maximally they flip, and that's the place where you won't detect them at all.
Yeah.
And then later on, you would detect in the place where it's going down, you would detect. So I'm guessing the place where you detect, they are not that many right-handed anymore. So they have gone back to some. So it's as if the right-handed are at a higher energy state, the left-handed are at a lower energy state. They kind of got excited, but that's metastable, and then they come back.
Yeah, but you know, the point is that diagram, the horizontal axis was not time; it was the impact parameter.
Yeah, but with impact, it doesn't have to be time, but with some kind of impact. So if a system is metastable, it means that in any a lot of parametric variations would not sustain that particular metastable state. So depending on your impact parameter, there is only a small kind of phase space where there's sort of, they just resonate or whatever, or the metastable thing is sustained. And everywhere else, there is just no way for it to sustain itself in this kind of metastable excited state, which is the right-handed helicity. Perhaps if there is some calculation that is possible at the level of kinetics and you can compute the energies, you may be able to determine whether this right-handed thing is metastable or not. And from there, you may get a reason for it. Because...
No, sorry, go ahead.
No, I'm just thinking about that.
Yeah, maybe in our future works, we should just look deeper in it, because we did the same thing in the background of gravitational waves, and we got this some oscillatory behavior, which wasn't weird. It was something that we expected actually from the beginning, but that one, it was really weird that I mean, when you go away from the center of the Earth, the probability increases, and at some point stops and then just go down. Everything is uniform. We assume that the Earth density is uniform.
I see.
So it was really hard to explain why that
I
happens.
see.
So in the end, we just blame the mathematics that it just works because the calculations tells us.
And if this is a potential candidate for dark matter, how much does it explain? I mean, because you know the mass, you know the probability of helicity flip. So if this was a viable candidate, does it really explain 100% of the missing mass or what?
No, I don't think so, because it only happens in a very finite region of the space-time. We outside the we computed for particles moving outside the planet or black hole or anything, and the probability it's really small. So
Oh, then it won't.
close
Then
to
it's not a
zero.
good candidate. Then it's not a good candidate.
No,
right?
I
It's
don't
not.
think so.
It's not going to explain the rotation curves of galaxies.
No.
Okay,
I mean,
so
based on our paper, no, but
okay,
some people are serious in taking just hot dark matter, the candidate of the neutron, let right-handed neutrinos be the candidate for hot dark matter. So yeah, but the modified theories of gravity was always more convenient to me to just assume that there
right.
is dark matter and dark energy. So yeah.
Okay. Further questions for Reza? Then let's go to Jacopo. So let me just start then. A lot of your talk had this, I would say, physically relevant, but also philosophically interesting question: what is charge? And you tried to provide some answers. The one part I got little confused about is whether you want to say that charge are just the generators of the gauge group, or I thought it would be more convenient to say that the charge were just the Cartan generators, so only the fully commuting ones, and that way they would just be the eigenvalues, the charge states themselves being the eigenvalues of the Cartan generators. Then you don't have this problem of explaining too many things, because with the SU3, you have two Cartan generators and they have three eigenvalues. There may be a simpler way to do that. So how exactly do you want to answer the question, what is charge?
Well, I think maybe I was just not but like I wasn't very linear in how I explained it. But yeah, that's exactly sort of what I was thinking, that the charge, if we think in terms of physical observables, the charge, for example, in the SU3 cases, can only be those like
Your sound is attenuating a bit. Maybe if you come closer or something. Yeah.
I have it here. It can only be those two eigenvalues that you can get from the two Cartan generators. So in a sense, like
So the sound is a bit bad. I mean, I'm not sure. For the others, how is it?
Can you hear me now?
Now it's better. Yeah.
Okay, I guess my earphone has some problem. But like the Cartan generator, the eigenvalues of the Cartan generators, I think those are the ones that are like the physically relevant charges, because then they also correspond to the weight that is one component of a possible representation that a particle can be in. Because for example, the quarks, you can have red, green, and blue. That's the fundamental representation, and it has 3 degrees of freedom, which are the 3 quark charges. So in that sense, it sort of fits together in this weird way. Like the numbers seem to not make sense almost, but the structure, like, because the numbers seem to not make sense, that like, okay, you have 8 generators, 3 charges, 2 non-commuting generators, but the way it fit together is that the two non-commuting generators define your weight vector, and then you have 3 weight vectors for the fundamental and 3 for the anti-fundamental. Plus, there's one small thing I'm a bit unsure about, which are the other 2 charges, which are essentially you would get like because the Cartan generators themselves, they commute with themselves. They so their weight is 0. And that is, if you consider the adjoint representation, like if you generate an adjoint representation by taking the tensor product of a fundamental and an anti-fundamental, then you get the adjoint representation and you get a trivial representation. And those correspond to the 8 gluons plus 1 extra degree of freedom that is not in the adjoint. Or if you had U3, actually, those will all be, I guess that's the adjoint of U3. Yeah, well, U3, then you would have 9 degrees of freedom. But like the central one, how can you think of charge for, let's say, the whatever is sitting at the origin? I guess it's just, I mean, it does coincide with electromagnetism, because if you have a U1, then it's just sitting in it's just a Cartan, something commuting, and it's sitting alone. So I guess that's just, no, it makes sense. You would get, right? If you had U1,
I mean, with the gluons, you have these linear combinations of the colors, and there are in fact 9 of them, one of them being dependent. So that's how your 8 plus 1 comes.
Yeah. So if you had U3 instead of SU3, you would have an extra Maxwell like an extra photon like particle, right?
Well, I mean, this is at the level of color, right? Like the gluons, they don't have one color. They have a combination of colors, right?
If you had the gauge group was U3 instead of SU3,
yeah,
you would have 1 extra degree of freedom.
That's right. That would be the electromagnet. You have a U1, it would be SU3 cross U1, indeed.
Yeah. Oh, right. You can think of it that way, then yeah, it's obvious.
Yeah. There may be a little more to make out of this to carefully understand this, because this is a nice way to think of charge very generally. And if one wants to then generalize this concept and go not to Lie algebras, but to higher Lie algebras and those things, what
Right.
one means by charge itself can nicely get generalized. Okay. Nice.
I also, one nice thing, just to add, sorry, I find that it in a sense, it doesn't have, like, this phenomenon seems intrinsically quantum in a way, because like if you consider the non-commuting generators, etc., those would correspond to physical states, the commuting commuting eigenvalues, simultaneous eigenvalues. But in a sense, all the group theory and everything it doesn't need quantum mechanics, right? So it seems there's like some information about quantum mechanics is just intrinsic in group theory.
It's fundamentally discrete. Yeah. That's that. I mean, or in other words, one may say that when we say quantum mechanics is discrete, we are really talking about it as just coming from the group theory, if the group theory is really fundamental.
Yeah.
Okay. Yeah, that's a kind of opposite way to think of it, but interesting. All right, great. Then in the few remaining minutes, let's go to Shraddha. Questions for Shraddha? Feel free to just speak up. You don't have to wait. So then, okay, let me at least start, and then hopefully others can join in too. So these optical lattices, when you are constructing them, so correct me just so that I got the idea of what you're doing. You had this initial single lump of the Bose-Einstein condensate, and then you were pumping it with the laser and the retro laser, and through that you were constructing some excited states, which are momentum states, and that was forming a optical lattice, or that was forming some kind of lattice within your cavity chamber, physically, literally being a lattice, right? So, okay, now on this lattice, you are then writing down an effective Hamiltonian. Now, that's the part I got a little confused, or rather I didn't understand. Your effective Hamiltonian had these operators which looked like you are talking about some quasi-particles on the lattice. So how should I think? How should I relate that Hamiltonian to this lattice? Because I'm thinking of maybe you have some quasi particles and the interactions, and it's not the Hubbard model, but it was almost looking like one. And so show me the mapping, show me the dictionary.
Yeah. So the operators that I showed you and denoted the lattice site. So and then so I guess like say you just had a pair of lasers and you wanted to make a two-side lattice. So now so you'd have only one term in the Hamiltonian, which is C1 dagger C0, which means that, you know, the initial state was at 0 h bar k. Sorry, it would be C0 dagger C1. No, sorry, I said it correctly the first time. But the point is that when you have this lasers on, some of the atoms will be transferred to the state labeled by 1. So that's why it's like C1 dagger C0. And then if you had other lasers on, the atoms in state labeled by 1 would be transferred to 2, and so on and so forth. I think so. It is very similar to the Hubbard model, but the Hubbard model also models the interactions between these particles at different sites. But tight binding Hamiltonian is a very sanitized, non-interacting version uh, of solid state physics. So we're just assuming that they are single particles; they don't talk to each other at all. So yeah.
But why are they advantages then for engineering if they are not talking to at all to each other? You
Yeah,
might as
so
well take something that does do the talking, right?
yeah. So actually, it turns out that they do talk because they are
Okay.
colliding with each other continuously. And so in that case, you might have heard of the equation, the Gross-Pitaevsky equation. And like you assume that there is a mean field, and this interaction is like a mean field because of all other lattice sites, and that's how people usually model it then.
Okay, so they are dynamic. It's not a stationary lattice.
Yes, things are all moving, the atoms are all colliding with each other.
Okay, so again, nice question from my side. If they are not interacting in the usual sense, but they are still colliding, how would this be different, except for the quantum mechanical aspects? How would this be different from a hard sphere gas, which is also just collisions and no other kind of attractive interactions?
You're asking like why can't we model this as a hard sphere gas? Is that
Yeah.
I guess was someone saying something? No.
No.
I think the quantum mechanical part is that now these these atoms are all in the ground state of the trap, and they just follow a different kind of statistics. So they follow
see.
Bose-Einstein statistics. So it's not a Maxwell-Boltzmann
Okay.
distribution. And I think you had a second question also related to this.
No, that was it. I was just thinking about that.
And actually, it's not a naive question because to answer your question slightly indirectly, right? Like what matters is the relative energy scales of the system. So, you know, there is some interaction energy. And in the experiment, we can control the tunneling from one lattice site to the other. So if we make that too high, we can ignore the interactions. So usually that's the regime we work in. If we make the tunneling small, then we actually have to account for the interactions, and then we just assume that it's all mean field. Yeah.
But to get a reasonable mean field, you may require a sufficient number of sites, right? Because if it's not too high, then mean field is not exactly going to work.
Yeah, yeah, but you'd be surprised by how much you can get away with just
Okay.
this mean field also.
How many sites you have?
I think the maximum in experiment is like maybe 20 sites.
And mean field works fine for that.
Mean field works fine for that.
Okay, okay, I see. Someone was saying something. Sorry, go ahead.
Yeah, I just have two questions. So the
Yeah.
first one, so in the Hamiltonian, you were actually talking about like actual electrons hopping from one side to another, or is it some sort of a quasi-particle, or dressed electrons, as in like Fermi liquid theory or something like this?
Yeah, so that's a really good point. So what we want to do is mimic the the electrons going from one side to the other. So we want to mimic real materials. The problem is that real life is very, very uncontrollable and dirty, right? The real materials you get, they are just not controllable at all. That is why that's what my experiment addresses. So these are actually now atoms hopping from one side to the other. And in some sense, they are mimicking the electrons in the real system. The nice thing about this system is that it's in an ultra high vacuum and you can control everything and study everything, piece by piece. So it's kind of like I don't know, I'm not a theorist, but perhaps like a theorist's way of understanding physics rather than an experimentalist.
No, that's
It's an emulator. It's emulating the system, literally an emulator, not even a simulator, but an emulator.
But in this emulator, you can change so many things so controllably that you can study, okay, if I change this tunneling right here, what happens to the system? So that in that way, it's pretty nice.
Yeah, so the other question is, in the Hamiltonian, you showed that you're mimicking, or you're getting in this hopping, there was like a phase.
Did he freeze?
Yeah, I think he
Okay,
froze.
we just gave him a minute.
Yeah. But I think I can anticipate what he's going to ask.
But he won't be able to hear if you answer it. So let's wait.
Yeah. I think he's going to ask about gauge fields and tunneling
Okay.
phases and stuff.
Yeah. That's a long pause. What happened?
Maybe he's
Anyone else wants to ask in the meanwhile about Shraddha's experiment? Oh. Okay, we'll give him 1 minute, and if not, then we may have to wrap up and take the discussion to Discord.
Yeah, I'll reach him out on Discord and ask.
Okay, fine.
What his
All
question
right. In that case, thanks everyone. This was great. It was really nice listening to all these short, but actually rather well presented and sufficiently detailed presentations. So the purpose of it was to really know in a little more detail what each of you do, and when you'll know, maybe in future you may, if you have in your something in your own work, you may know who to ask what. So thanks everyone. It was a nice learning experience for all of us. And with that, we'll get back to project work. Some of you on the channel, I'm seeing you after, so keep ready. I'll send you a message.
Yeah.
All right. Bye-bye.
Bye.